Excellent. So when we leave Design Modeler, we go back to Workbench, and the next stage is to sort out, well, what's left. And all that happens in the next piece of software that's called Mechanical. So to access this, you simply need to double-click or right-click on the model. Okay, so right-click and edit or double-click. So that's starting the software called Mechanical. You can see that. So it's a good idea to check at the bottom. So it takes a few seconds, and we are going to get into the interface. So that interface, indeed, is going to allow us to do a few things. Sort out the mesh, so the model. You can see there is a mesh here. Sort out the boundary condition. They call it setup here, but it's done in one go in Mechanical. And sort out the results we want to obtain. Okay, so it takes a little bit of time to start. It's going to give me slightly different, more modern interface. It has been updated a couple of years ago, I think. So what have we got? What have we got? Well, yeah, kind of a usual interface, really, similar sort of idea. So we can see the model here, the big window, the big panel in the middle. So you can do the usual. You can faff around to see what you can do. You can zoom. You can do everything. A lot of it you can obtain from here. Otherwise, you can play with your mouse and the different buttons do different things. Okay. Right. Anyways, that's not the main point. What have we got in the project tree? So we have got a model, and the model contains geometry. So the geometry. If we click on the plus, it updates it. So this is a solid. Okay, it has various things. I'm not going to look at it yet. It's solid, and at the moment, what I'm checking here is that the assignment it's made of structural steel. So can I change that? Indeed, I had said I wanted it to be made of alloy, so I change the materials. Okay, so now it's made of alloy. So you just change that here. Next stages are meshing. We need the mesh to create the elements themselves. Then we need to add the boundary conditions, so the loads and the constraints, and finally we need to tell Mechanical what we want to calculate. Right, so let's do that in order. So if I click on mesh, well, you can also obtain from here. So you get different options and different properties. So you get every time you can something about properties there. Right, I'm going to do a very quick job because we just want to get going to see how things work. So just going to generate a basic mesh. So we just click on generate, and it has made a mesh for me. So that is the mesh. It's a terrible mesh. Well, it's not a very good mesh. It's not very fine, and that's what it looks like. So each of these things is an element, and at the corner is a node. So what is quite useful is to check the statistics, and tells us that I have got around 1700 nodes and a bit less than 300 elements. The free version of ANSYS can only do 32,000 node elements. So I can't really improve things there. So let's improve that mesh. Okay, I have a bit of leeway here. So I can do different things. So the easiest is to go directly into it and to change the default size. Let's say I put 5 millimeter. All right, so the mesh is now obsolete. So I need to update it. Click on mesh. It doesn't change very much, isn't it? A little bit. So 5 mm is not good enough. Let's do a 2 millimeter mesh. That's going to be a lot smaller. But let's try that. Update it. It takes a little bit of time with this calculation. I've got a finer mesh. I'm not saying it's a perfect mesh at all, but it's not bad actually. It's quite. We'll discuss meshing a lot in later, because meshing is very important. Good mesh makes a difference between quality results and poor results. But what have I got here? Ooh, starting to be, yeah, I still have enough. So I'm going to keep that mesh. Okay, it's going to slow my calculations a little bit, but that's a decent mesh. Now, I've just generated here. Okay, we'll see how to do. There are many things we can do, much more. But I just want to do basic things at this stage. Okay, great. Having a mesh, I now need to create, well, the setup, which means how is this part mechanically connected to the rest of the world, and how is it loaded. So the brackets, so you go into static structural, and that brings you the environment tab, and you've got a lot of options. You can add supports, like I call constraints, and you can add loads. Alternately, if you want to be faster, you can right click, insert, and I will want to add a fixed support. That's one of the simplest. There are a little bit of information. Let's not bother at the stage. You can do that in your own time. You select a face, so I'm in the selecting face here. I could select an edge or a vertex, but I want a face. I select this face. I apply it, and that's it. It's a fixed support. There's nothing else to say. It's fixed. Okay, great, fixed support. What else do I want to do? I will create a load. So right click, insert, and I will just do directly a force. Insert a force. There are a lot of other things you can do. A lot, and you can explore that later. We'll choose some of these in the subsequent tutorials. Right, a force. So it can be defined by a vector or by components. By vector or by component. So vector, simply you choose a direction. First of all, select the geometry. So I remember we created that imprint there exactly for this purpose. So I apply it here. And the component, let's give it a value. Let's give it a value of 2 kilonewton. Okay. And going that way. Okay, fine. You can change direction. You could change direction by, for instance, could change direction. Select that one, for instance. You can apply it. You can see how it will. But I want it to be perpendicular to that. So I'm going to change the direction back to it, but it guessed it was perpendicular to that face, and I want to change the direction. So I swap on that arrow. Okay, so I swap it and I apply it. I want it to push and not to pull. Okay, great. You will see that more often than not, you might want to define it by components, and you can give three coordinates in the X, Y, Z. Again, experiment with that. Okay, so I've got a support and a force, so things will happen, which is cool. Okay, that's enough. We have the basic conditions for it to solve. Let's solve them. Let's solve. Okay, so it's going to tell you a little bit. It's going to run a calculation in the background. It's kind of things that we will see in the actual lectures. So and it's done. So you can see that even with around 20,000 nodes, it's actually relatively quick, and my computer is not the fastest. Okay, great. What have I done? I was silly, and I totally forgot to tell it what I wanted. So it has calculated things in the background, but it does not display. In order to do that, you need to add what they call solutions. So we can add deformations, strains, stresses, different kind of stresses, various other things. Or again, you can right-click, insert. So it's common to have a total deformation, so that you know by how much every node is moving. Okay, now we need to solve that, of course. And I also will insert a stress, and I will insert ANSYS, and I also will insert maximum principle. Now, ANSYS is a usual default. If you remember from the end of the stress analysis course last year, that ANSYS is useful because it allows you to compare directly to the yield strengths, and that tells you whether it's useful for failure criterion. There are others, of course, the maximum shear stress, and all these things. Of course, ANSYS and maximum shear are only really meaningful for ductile material. Now I have got solid copper, and that is indeed very ductile. If you have got brittle materials, other failure criteria might be important, and you might want to apply something. And there is a lot of choice. There is an absolute huge amount of choice. And in fact, when you analyze, and I think you very often will want to have more than one type of stress to try to. Anyway, so again, I'm getting ahead of myself. We'll see some of these details at a later stage. But here, well, how do I visualize these things? Well, I need to solve. Now it's going to be a lot faster because it simply needs to do some post-processing here. All the calculations, the matrix is already done. Okay, fabulous. So what is going on now? Well, I've got some pretty colors. And now I'm in the result tab. Okay, there are a lot of things going on. Okay, so let's plot the deformation first. So what we have is a colored legend here, and it's telling us that the maximum displacement is in red, is around 0.7 millimeter, and that is not shocking. It's actually totally understandable. Okay, we are pushing that way, so fine. Something else that I like to do is to show the undeformed wireframe. So that removes, of course, that removes the mesh, but I can always put it back. And it tells me, so this is fixed, and it shows how things have moved. So that looks a lot more than 0.7 millimeter, and that's because automatically it's scaling it so you can see it. So you have got different options. You might want to exaggerate deformation to highlight what's going on, or you might want to just plot it in a more realistic way. Okay, so that's more like it. So that is a true scale, and it's showing me the deformation. Okay, that's not the most useful thing, but okay. You've got the units there and so on. Let's check the stress. Now the maximum stress. Ooh, maximum stress at around 300 megapascal. Now, something you have to keep in mind very quickly is that you have to ignore the 0.77 here, okay, at the top. There is no way that the stress is accurate at that point. This is an approximate method. I've got a mesh. There's a mesh. The actual results, final results, will depend on the quality of the mesh. And in fact, we'll do that in the second tutorial. We need to, so it's called, do a convergence study to make sure that we can believe our numbers. But there is no way that my values that I can read from the solutions are accurate to 1% of megapascal. I mean, if it's accurate, you will see when we do these convergence studies, varying the mesh and calculate and plotting the values of interest as maximum stress. You will see how much they vary. So around 280, 285 megapascal. Okay, where is it happening? Well, it looks like it's happening here. Maybe here. I'm not sure exactly. So in order to know, you can add some probes. Let's put the maximum probe and the minimum probe. Not so important here. Okay, fine. Now, of course, being a von Mises, I don't have any sign. Let's have a look at the maximum principal stress. Maximum principal stress. So it looks like that the main issue. Let's put the maximum. So it looks like the main issues are possibly here in tension and maybe something here in compression. Not sure. And so there will be a lot of analysis to be done to actually check what is going on. Okay, just the pretty pictures are not enough. Still, that being said, if we were to maximum equivalent stress, this is probably too high for copper, so could change the material, or could modify the sketch. For instance, remove this hole or make it smaller. So that's where design comes into. But that's pretty much it. You can see how in very little time it is actually possible to run a simulation. I am not saying it's a good simulation. I think it's a bad simulation, right? At the stage, we need to do a lot more to refine the model to make sure that what we are doing is correct. But these are principles. So at the stage, yeah, please play around, modify things. Yeah, try it. Try the different supports, different loads, and so on. Okay. Right. As usual, any queries, please use the forum. Oh, and I must insist, try. Well, actually, no, don't try. Do the tutorial, the paper tutorial in itself. It will show you different loads and it's slightly different thing. Okay. Thank you very much.